Imagine walking out into the middle of the Sahara Desert, right? It's high noon, the heat is just shimmering off the dunes, and you stumble across a perfectly unmelted ice cube just sitting there on the sand.
Yeah, I mean, you wouldn't need to be a thermodynamicist to know that ice cube didn't form there over centuries. The environment is just entirely hostile to its existence.
Exactly. It had to have been dropped there moments before you arrived.
Sure.
And today, we are looking at a discovery in deep space that is basically the astrochemical equivalent of that ice cube.
Right. We are zooming all the way in on something completely microscopic, practically invisible, really, that actually has the power to rewrite a massive cosmic timeline.
Welcome to the deep dive. Okay, let's unpack this. Our mission today is to examine an incredibly specific set of samples brought back by the Japanese Space Agency, or JAXA, from their 2018 Hayabusa 2 mission.
Yeah, and we're working from a piece published by Adrian on May 22, 2026, over on techno-science.net.
Right, which breaks down some staggering findings originally published in the Astrophysical Journal letters. We are looking at a microscopic layer of sodium on a distant asteroid named Ryugu.
And we're figuring out what that chemical anomaly, tells us about the violent hidden history of our solar system.
To really grasp why the astrochemical community is buzzing about this, we have to establish the physical nature of the evidence, right? Because the Hayabusa 2 mission wasn't just a matter of landing and scooping up some loose dirt.
Oh, not at all. The probe had to perform this highly complex kinetic sampling maneuver. It fired a tantalum projectile into the surface of Ryugu at, well, hundreds of meters per second.
Wow, just blasting it.
Yeah, intentionally fracturing the bedrock to kick up pristine subsurface ejecta. And then that ejecta was caught in a specialized collection horn.
Which means the material they brought back to Earth in 2020 wasn't just like surface dust that had been floating around. It was securely anchored material.
Precisely. So scientists took two specific fragments from those return samples and subjected them to advanced spectroscopic analysis.
Right.
And this analysis was designed to study layers of material just a few nanometers thick. And on the absolute outer edge of these fragments, they found a distinct, continuous film of sodium.
Okay, wait. I have to jump in and push back on this premise just to ground the physical reality of what we were talking about here.
Sure.
A nanometer is absurdly small. I mean, we are talking about a layer of material that is practically non-existent. It's a fraction of the width of a human hair.
Yeah.
How do we know this isn't just, random space dust or terrestrial contamination?
That's a very fair question.
Because the Hayabusa 2 reentry capsule landed in the Australian outback. It had to be transported to a lab. And before that, the probe itself was firing chemical thrusters all around Ryugu, not to mention firing that bullet you just talked about.
Right, the tantalum projectile.
Yeah. Finding trace sodium could so easily just be an artifact of the collection process, couldn't it?
Well, contamination is absolutely the nemesis of sample return missions, and the researchers actively hunted for it. But the morphology of the sample totally rules out a laboratory artifact or thruster exhaust.
Oh, so?
Because they didn't just find isolated atoms of sodium passively resting on the surface. When they mapped the nanoscale topography of these specific fragments, they saw a deeply battered terrain.
Okay.
The surface was heavily pockmarked with microscopic impact craters, like these tiny, violent bowls carved into the rock. And crucially, lining the inside of those craters, they found glassy melt structures.
Oh, wow. So the rock didn't just fracture, it actually underwent flash melting.
Exactly. You don't get silicate glass on a frigid asteroid without a massive instantaneous injection of thermal energy.
Right, a bump from a robotic arm or like exposure to Earth's atmosphere just doesn't generate that kind of localized heat.
Exactly. Those microcraters and the surrounding melt glass prove this sodium is inextricably linked to a hypervelocity impact event. These fragments were essentially sandblasted by a swarm of micrometeorites traveling at tens of thousands of miles per hour.
That is insane.
Yeah, the sheer kinetic energy of those tiny impacts converted to heat so rapidly in the vacuum of space that it vaporized the surrounding rock and left this sodium-rich melt behind.
So the surface of this asteroid, it's basically an active war zone, just scaled down so far we miss it.
Yeah.
That totally establishes the physical reality of the sample.
Right.
But the core scientific contradiction of this whole paper hinges on the chemical nature of sodium itself.
Oh.
Finding it shouldn't just be difficult. I mean, in that specific environment, it should be chemically impossible, shouldn't it?
What's fascinating here is the insight from Ernesto Palomba. He's a researcher from the Italian National Institute of Astrophysics, and he really anchors these findings.
Okay, what does he point out?
Palomba points out the glaring thermodynamic issue. Sodium is a highly volatile element. Out in the vacuum of deep space, on a completely airless body like Ryugu, a volatile film like this has absolutely zero protection.
Right, because there's no atmosphere.
Exactly. It's subjected to constant thermal cycling, extreme ultraviolet radiation, and the relentless bombardment of the solar wind.
Just totally exposed.
Yeah. And under those conditions, atomic bonds break down. The sodium should sublimate and be entirely dispersed into the vacuum of space. It simply cannot stick around on a geological timescale.
Here's where it gets really interesting. Because going back to the ice cube in the Sahara analogy, it is all about the passage of time.
Precisely.
If the laws of thermodynamics dictate that sodium cannot survive exposure to the solar wind, and yet we are looking at a pristine layer of sodium glass on this rock, well, the only logical deduction is that the event that created it just happened.
You nailed it. The survival of the sodium is the astrochemical equivalent of finding fresh DNA in a fossil. It proves the micrometeorite bombardment was incredibly recent. Based on the known degradation rates of volatile elements under solar radiation, the researchers calculate that Ryugu didn't undergo the sandblasting millions of years ago.
So when was it?
It flew through this dense cloud of micrometeorites a mere 1,000 years ago.
1,000 years. Wait, in cosmic terms, that is quite literally yesterday.
It really is.
I mean, while Ryugu is getting utterly pulverized by this invisible swarm of space debris, human beings were navigating by the stars to cross the Atlantic. The Vikings were establishing settlements.
Yeah, it puts it right in our historical timeline.
We usually treat the asteroid belt like this static, ancient museum of the early solar system, but this completely shrinks the timeline. It proves these bodies are undergoing catastrophic topographical changes in our own modern historical era.
It absolutely moves asteroid evolution out of deep time and into real time. But the presence of the sodium only gives us the maximum possible age of the impact.
Oh, I see. Because it's still there.
Right. To confirm that 1,000-year timeline, the researchers couldn't just rely on what hasn't disappeared yet. They had to interrogate the secondary evidence left at this microscopic crime scene.
They had to look at what was actively being created.
Exactly.
Because a hypervelocity impact in a vacuum is going to trigger a cascade of secondary chemical reactions. You can't just date an entire celestial event based off a single data point like missing sodium.
No, you really can't.
So what else was in the spectroscopic data?
Well, alongside the sodium melt pools, they found a highly localized enrichment of metallic iron directly on the surface of these fragments.
Metallic iron. But asteroids obviously contain iron anyway, right?
They do, but it's typically bound up in silicate minerals like olivine or pyroxene. Finding an enrichment of pure nanophase iron right at the boundary layer of these craters is the hallmark chemical signature of space weathering.
Space weathering, okay.
Yeah, it is the physical scar of the solar wind interacting with the freshly exposed rock.
Can you walk me through the actual mechanics of that? I mean, how does the solar wind pull metallic iron out of a solid rock lattice?
It's a process called ion sputtering.
Sputtering, okay.
Yeah. The solar wind isn't like a gentle breeze. It's a relentless stream of highly energetic protons and electrons ejected by the sun, traveling at hundreds of kilometers per second.
Wow.
When those charged particles smash into the freshly melted, sodium-rich glass on Ryugu, it is like playing kinetic billiards at the atomic level.
Right.
The protons violently knock atoms out of the mineral lattice. The later elements, like oxygen and magnesium, are easily ejected and escape into space.
But the iron is heavier.
Exactly. The heavier iron atoms are left behind. And as the lighter elements are stripped away, those solitary iron atoms coalesce on the surface into tiny metallic nanoparticles.
Oh, I think I see how these two distinct clocks are ticking together. Let me try a real-world analogy.
Go for it.
It is like finding a dented car bumper. The dent itself is the microcrater. But if you look incredibly closely inside the crease of the dent, you find a very specific type of localized rust forming on the exposed steel.
Yes.
That rust, the iron enrichment, tells an insurance investigator exactly what kind of corrosive weather the car has been subjected to since the collision occurred. The dent is the violent event, and the rust is the timeline of exposure.
That captures the mechanics perfectly. The initial micrometeorite strike flashed the rock into glass, which reset the clock.
Right.
Then, for the next 1,000 years, the solar wind began bombarding that fresh crater. By measuring the sodium that hasn't sublimated yet against the volume of iron nanoparticles that have just begun to accumulate through sputtering, Scientists can cross-reference the chemical degradation.
That is brilliant.
They aren't guessing at a 1,000-year timeline. They are reading two simultaneous intersecting chemical clocks. It is just an incredibly elegant piece of astrodetective work.
So what does this all mean? We've essentially decoded a forensic history of an airless rock millions of miles away.
Yeah, we have.
But astronomy is ultimately about understanding our own context. How does decoding Ryugu's violent weekend 1,000 years ago change our understanding of the neighborhood we actually live in?
If we connect this to the bigger picture, it fundamentally reshapes our situational awareness of near-Earth space. We tend to visualize the inner solar system as a mostly empty void, with a few planets and inert asteroids orbiting in peaceful isolation.
Right, just floating quietly.
Exactly. But these nanoscale craters prove the void is highly active. It is crisscrossed by invisible, high-velocity rivers of debris left behind by disintegrating comets. Ryugu didn't just have a random accident.
It didn't.
No, its orbital path intersected directly with one of these dense cometary streams.
Wow. Just visualize the sheer sensory terror of standing on the surface of Ryugu when that intersection happened. You were standing on this pitch-black, diamond-shaped rock in the absolute vacuum of space.
With no atmosphere.
Right? No atmosphere, so there is no sound. No atmospheric friction to provide a warning glow. Just an instantaneous, silent sandblasting. Millions of tiny projectiles slamming into the regolith at tens of thousands of miles per hour, kinetically flash melting the ground beneath your boots.
It sounds like a sci-fi nightmare.
It does. But the mind-bending part is that Earth is flying through those exact same cometary streams, isn't it?
We absolutely navigate the exact same hazards. The difference is solely atmospheric. We intersect with these dense trails of cometary dust on a highly predictable annual schedule.
But nothing hits the ground.
Right. When a swarm of those exact same sand-sized meteoroids slams into Earth's thermosphere at 60 kilometers a second, the atmospheric ram pressure is so intense that the air in front of the particle superheats into a glowing plasma.
Oh, I see.
The meteoroid completely vaporizes miles above our heads.
So the violent kinetic energy that permanently scars the bedrock of Ryugu is safely dissipated by our atmosphere into glowing ionized gas.
Yes, exactly.
We literally sit on picnic blankets in August and watch the Perseids meteor shower, making wishes on the exact same cosmic sandstorm that turned Ryugu into a microscopic war zone.
That's a beautiful way to put it.
It really brings home the brutal utility of having a thick atmosphere. We are completely insulated from the true kinetic violence of the solar system.
The contrast in how different celestial bodies process the exact same physical event is really what's driving the next major leap in this specific field of research.
Oh, where's the research going next?
Well, now that the team has successfully reverse-engineered Ryugu's history from these return samples, they aren't satisfied with just passive observation. They want to move to active, real-time experimentation.
Wait, you can't exactly charter a flight to an asteroid during a meteor shower just to watch it happen. I mean, how do you actively experiment on a 1,000-year-old cosmic event?
You build the cosmos in a lab.
You kidding?
No, really. The researchers outlined in the journal that the immediate next phase is to reproduce these exact chemical modifications empirically. They are sourcing analog materials.
Like fake asteroid rock.
Sort of. Terrestrial rocks and synthesized minerals that perfectly match the spectroscopic profile of Ryugu's carbonaceous regolith. They will place these analogs inside ultra-high vacuum chambers and systematically subject them to simulated space weathering.
The engineering calibration required for that is just staggering. I mean, they are trying to accurately bottle an invisible 1,000-year-old cosmic sandstorm.
It is incredibly difficult.
To simulate the solar wind sputtering, they would have to bombard the rock with highly tuned ion beams to match the proton density of the sun.
Yep.
And to simulate the micrometeorite impacts, I mean, you can't just hit it with a tiny hammer. You would need high-power, femtosecond pulsed lasers to artificially recreate the exact thermal shock and flash melting of a hypervelocity impact.
And they have to calibrate those lasers and ion beams perfectly. They need to see if they can generate the exact same nanometer-thick layer of sodium-rich glass and iron nanoparticles they found on the Hayabusa 2 fragments.
That is wild.
If they can successfully replicate the chemical timeline in real time, they won't just be proving their theory about Ryugu. They will be fabricating a universal Rosetta Stone for the entire solar system.
Because if you establish the exact mathematical degradation rate of these materials in a lab, you can just apply that formula to anything.
Exactly.
We wouldn't be guessing at the history of airless bodies anymore. We could analyze a microscopic core sample from the asteroid belt and instantly read its entire timeline of kinetic collisions.
It changes everything.
We started today talking about our bias toward the macro, our obsession with galaxies and supermassive black holes. But a practically invisible smudge of sodium, just nanometers thick, completely shattered our perception of an asteroid we thought was a static, ancient fossil.
You really did.
It proved that deep space is dynamic, it's violent, and it's actively rewriting its own geology on human timescales.
It proves that the history of the universe isn't just written in the grand orbital mechanics of the planets. It is recorded in the nanoscopic fractures of individual grains of dust. We just needed the engineering audacity of a mission like Hayabusa 2 to go out there, grab the evidence, and bring it back to the lab.
And as we close out today, I want to leave you with a final thought to ponder. If a 1,000-year-old micrometeorite swarm left such a mathematically precise, readable chemical signature on the surface of Ryugu, what kind of microscopic warning signs are resting on the surface of our own moon right now? Or even etched into the solar panels of our artificial satellites orbiting Earth, just waiting to be deciphered? If we can master this laboratory science, could decoding those nanoscale impacts warn us of shifting, dense micrometeorite clouds before they cross Earth's orbit?
That's a fascinating thought.
Could looking incredibly closely at the scars of the past be the key to predicting the invisible cosmic weather of our future? Something to think about the next time you look up at the stars. Thank you for joining us for this deep dive. Take care.
Goodbye, and keep looking up.